Topics we're talking about now is significant figures or significant digits. Significant figures, who cares? What's very important, we get measurements as close as we possibly can in many different sciences, such as engineering and chemistry. It could be the difference between life and death. Knowing that a remeasurement has a degree of uncertainty, we have to be as precise as we can. Now, the measurement that we have depends on the least accurate measuring device. So we talked about that when we talked about accuracy and precision with the beakers, the graduated cylinders, the meter stick. So here's an example. We have 4 graduated cylinders, and up here it says what we can measure it to. So the precision here, or the accuracy, we can get up to 10 milliliters on this one, 5 mils, 2 mils, and 2 mils. And there's even some that can get much, much more accurate. Your accuracy depends on what instrument is being used to measure. So if we're measuring something down here, we can get down to the 2 milliliter in accuracy in this one, but we can only get down to 10 mils of accuracy here. So when we report our answer and our data and our findings for this one, it can only be accurate to 10 mils as opposed to 2 mils for this one. Significant figure rules, we'll go over these one at a time, but I'm just going to give you them all at once now. The rules here for counting significant figures. The first 2 rules are probably the easiest. Non-zeros are significant. This is easy. If we see a non-zero, it's significant. That means 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these are all significant. There's a non-zero significant. That's pretty straightforward. The tricky part of significant figures is really dealing with the zeros and counting the zeros as being significant or not significant. So the second rule is a pretty easy one when it refers to a zero. All captive zeros or zeros between non-zeros are significant. So for example, this is a captive zero. It's between non-zeros. So that means this zero is significant. So here we have 3 sig figs. It's between a non-zero. Or we might have this is significant. This zero is significant now. So it's 1, 2, 3, 4, 5, 6, 7. That is 7 sig figs right there. All right, so anytime you see a zero between 2 non-zeros, it's significant because it's there for a reason. That means these were measured to a certainty. This last one was really measured to a precision. Zeros to the left of a non-zero are placeholders and not significant. So for example, we might have 0, 0, 0, 0, 0, 0, 3. These are all insignificant, not significant. So there's only 1 sig fig, 1 significant figure there. Or if we just have 0.1, 2, 3, there's 3 sig figs. This is not significant. It's to the left of a non-zero. It's just a placeholder. It's something that we just put there to mark a place. Zeros to the right of both a decimal and a significant digit are significant. For example, if we have 2.0, this 0 is significant. There's a reason it was put there. The reason we put 2.0 instead of 2, because this place, it's a significant place. So this is 2 significant figures. 0.10, this is significant, this is not. So we have 2 significant figures here. 0.3, 0, 0, 0. all of these are significant zeros, as well as this is significant and this is significant. We have 5 significant figures because it's the 0 to the right of a decimal and to the right of a non-zero. Zeros at the rightmost end of a number but to the left of understood decimal point are not significant. It's understood that there's a decimal point there, but it's really not. So this is not a significant 0. It's there as a placeholder. So we only have 3 sig figs here. This is just a placeholder. Now if there was a decimal point there, it would become significant. Another example, the number 20, there's only 1 significant digit or figure. That also just has 1 significant figure. The understood decimal place, these to the right of the number but to the left of the understood decimal point, just 1 sig fig. So it doesn't matter. We could have 5 billion, still just 1 sig fig. Now if we have 3030, this is significant, of course. This is significant. Now the sandwiched 0 is also significant. So that's just 3 significant figures. So unlimited number, number 6. This is when there is no uncertainty in measurements. When you don't really measure anything, you just know. For instance, exact numbers. 10 students. We don't have to measure 10 students. We know there's 10 students. When we can count something like 10 students, that's no uncertainty. Another example is with conversion factors. So there's no uncertainty there. We know that 1 meter is about 3.3 feet. Now this comes into play when we're calculating significant digits and we're making measurements on something. We don't have to worry about the significant digits here. We don't have to say, well, 10 students is 1 significant digit. But that's not true. We don't take these numbers into account when we're calculating significant figures. Okay, so let's just practice these. The best way to learn all these rules is to practice and practice and practice. And you can find a lot of these things online. Just Google significant figure practice and you can come up with a lot of these fun little activities to do. And again, have fun with it. Invite some friends over. Get some chips and soda and you can have a party. They'll come over and say, hey, what are we doing? We're doing sig figs. And they'll forever be your friends and indebted to you, and you'll be the most popular person probably definitely in the school, but maybe in the city. So let's just look at a number here. So here we have 4 non-zeros, so that's easy. It should be 4. Okay, let's try another one. Now we have right of the decimal point, but we have non-zeros, that's 4 non-zeros, and we have a sandwiched 0, so that should be 5. And again, it's just knowing what these rules are. It's just practice and practice. The 0 ones are the tricky ones. Okay, so here we have 3 non-zeros, so that's 3. Now to the left, those are not significant. There's no non-zeros out here, so these are not significant. So we just have 3. Non-zeros, easy, 5. Okay, so there's a little more challenging. We have 3 non-zeros. We have a sandwiched 0. That's 4. And then we have 2 non-zeros, but they're, 2 zeros, but they're to the left. There's no other non-zero out here, so that's just 4. All right, so again, 4 non-zeros. Okay, so here we have scientific notation. And scientific notation is actually very easy. So remember, E, when we see E, it just means the power of 10. So this number is 4.1 times 10 to the negative 5th. Scientific notation makes it easy for us to do sig figs. All we have to do is count the numbers that are not in the power of 10. So it's 4.1. That's two numbers, so there's just two significant figures. It's really pretty easy with scientific notation. This is 2. Just looking for a... Okay, this is a better one. So we have 21.00. Now it's to the right of a decimal and to right of two non-zeros. So that means there are 4 significant digits. So there's a reason why those zeros are there. It's not 21, it's 21.00. These two significant figures, are significant. They're important. Okay, we have a sandwich 0, so that's 3. Right? To the left, those are just placeholders. We have 3 significant digits here. Okay, another scientific notation. So this is 7.2971 times 10 to the first. So anything that's in front of the power of 10, any full numbers in scientific notation is significant. So that would be 5. Oops, so in fact I didn't know I could do that. Okay, this is a 3. Alright, so this is more challenging. It's to the right, so we should have 5. Alright, 0.00901. That should be 3 significant digits. So, find some of these on the web and practice them. It's actually quite fun. Again, invite your friends over.